understand exactly where the arrows go or whatever, but interesting to know that interrupt comes in, finds a vector in the table, and the table tells you how to find the syscall handling code. So syscalls documentation is a little bit scattered, again, if you're trying to play at home. Section 2 of man generally will provide some C-style prototypes and some information on what the return value from a function that looks like this in C would be, number of arguments, the types of arguments, and things like this. However, finding the actual number of the syscall, so not like the number of arguments, but saying that this is syscall 4, that doesn't show up in the man pages. So you have to go find that somewhere. So here's some common locations in Linux. It might be here, in Solaris, and syscalls.h, and so forth. It also might vary depending on your distribution. You might have to follow your dependency tree and find them in there somewhere. All right, another kind of neat thing. Syscalls are pretty easy to observe. So take out your handy Linux box, open up an editor, and type in this stuff over here you see on the right. So we have a 32-bit assembly. We have a single section, a single global symbol. We push the byte 1. We pop it into EAX because we know that exit is system call 1. Got to stop doing that. And then we XOR EBX. So this is not really required. This is going to be the value that exit is going to return, you know, exit 1, exit 0, exit 2, so forth. So it's not really returned if you don't, it's not really required if you don't care what the exit value is. And we'll see some more examples of that in a little bit. And then you raise your software interrupt. You do your interrupt 80, which invokes the kernel handler for the syscall. So we'll compile that. Notice here we're using ELF because we're just going to actually execute it. We're not going to use one of our vulnerable programs to as a wrapper around this. So we can make it ELF, we can link it, and then we can use a program called strace, right? Really big, red, bold, whatever. Strace your executable, and that will just show you all the system calls. So it loads it, it does the exec.ve to actually get it executing, and then after that you'll see all the system calls that your OS does, and if they chain down, if one system call handler actually calls other system calls, you'll see those as well, right? It's tracing all of them. So this XOR of EBX on Linux is going to be the argument that makes this be 0. So if you were to set EBX to 2, this would change to 2. Then you see the strace process detaching. So very easy to observe. All right, so our first Solarisism. If you say it really slow, if you're a Solaris guy, Solaris background, if you're just drunk, maybe strace sounds like truss, all right? Strace in Solaris is a totally different thing, all right? So you need to use truss to get the strace-like functionality in Solaris. The build tools also are a little weird. For example, GCC is not in your path by default, so you have to make sure to add some things to your path. The assembler, AS, in my testing, it links against libc. We all know that GCC links against libc, so that's why we're not compiling our shellcode with GCC. We're just assembling it directly. But anyway, it seems to me, not being a Solaris background guy, maybe there's better ways to do it, but it seems to me that it's just easier to make your payloads on some other box and then transfer them to Solaris for testing. All right? So use NASM and then SCP them over or whatever. No? All right, so these are not the man pages you're looking for. Every distribution is different. There's very little continuity from man pages from system to system. Generally, distributions kind of keep it the same, but they don't have to. So Solaris has different sections. To specify the section, you actually have to use the -S option on the command line to get to the different sections. And then there's also subsections, right? So 3C would be the C library in man section 3. This is useful because a lot of man pages you're looking for will at first appear to be non-existent because they're not where you think they might be. So you might need to get familiar with sections like 3socket and 3C to find what you're looking for. Widely useful is to know that man in Solaris has a -L option that will list all the sections of a string. So if you say man L socket, it will list wherever socket comes up in any man section. You can find the subsections that you're looking for. Okay, so versions of Solaris. I have no idea who's in charge of the versioning scheme, but so we have stable releases. Solaris 10 is what they're called. So it comes out in December of 05. January of 06, they decide to add Grub. June of 06, they add ZFS and other things. Right? That's not the only edition, but that's like kind of the main one as I scan through what they do. So they have all these releases that come out, and they kind of just name them after the date. So you could have Sun 10 606, and you could have Sun 10 1106, and they're different. They're both Sun 10, but that's how they name their stable release, their editions. And then totally independent of that, you have development releases. They call this the Express Developer Edition. And from what I can tell, basically what happened is people wanted to try Solaris. They hear that Solaris is the next thing. The contractors like them, the government likes them, whatever. They want to learn Solaris. They download Solaris 10, and they don't have anything that they need. All the tools that they're familiar with, and nothing works the way they want to. So Sun makes this development edition. The development edition has all the stuff that you really want, right? It has the build tools built in and everything. So think of this as Red Hat Enterprise and Fedora or whatever. Two different trees. And then kind of independent of that, there's now also a project called Open Solaris. So Nevada, Solaris 10, Solaris Next, Open Solaris, they're all pretty much acronyms for the same thing. Developer Preview, they all have different distributions of Open Solaris. So all these different things going on. Found this slide somewhere buried in a Sun PowerPoint deck. And it kind of shows you the development cycle. A little weird, but basically for our purposes, we see features go into the development train. Sometimes they get bounced back out and they go into this Express Edition, so they can make people think that they're going to like buying Solaris 10, even though those features never actually end up in release. Again, Red Hat versus Fedora, right? But some features hit the development train, and they actually filter through and they make it into the stable release, right? So the idea is that the important one is this yellow arrow down here, where we have new things that come into Solaris 10 as opposed to just updates and bug fixes and stuff. Oops. All right. So like many OSs, Solaris claims to have some level of POSIX conformity. All right. I don't know what the last OS is that claims total conformity. But anyway, Sun's really nice. There's actually a man page that delineates out that this version of Sun OS does these things in a POSIX way, and this version of POSIX and everything. It's pretty nice. Most OSs have a very transparent layer. So POSIX gets translated down to the system call, and there's not much in that translation phase, right? It's kind of a pass-through layer. Check out the differences between C prototypes and in sections 2 and 3, and like how the calls actually work. There's very little translation that has to happen there in most OSs. So Solaris is taking advantage of this abstraction layer, and they're saying, we'll provide you this API to the higher level, and we will then actually perform the actions however we want down at the lower layers and accomplish the same goal. So for example, Solaris didn't used to provide an interrupt for performing syscalls. So shellcode and everything else is formed to use sysenter exit or the farcall method. So you have to do one of these constructive methods. So now, it's relatively undocumented, but there's an interrupt 91. So it's not in 80, but it's the same thing, right? It's just an interrupt that's a vector into the IDT. The calling convention smells a lot like BSD. So you push your arguments on a stack, you put your system call number in EAX, and then you raise your software interrupt. Note, sometimes additional things come back in something other than EAX. So if you're looking for register state to be preserved across system call, that might not actually happen. So you just have to be cognizant of that in your testing. All right, so the original Solaris 10 release used the farcall method. Later S10 updates includes this int stuff. So I don't know exactly where that happened. Digging through all of this is not my idea of fun. Plus, you can't find some of these older releases. You go to the website, you have to log in and register before you can download it anyway. If somebody wants to actually donate me all of these exact versions that have ever come out of S10, maybe someday I'll get to it, but still not a very interesting. But anyway, sometime in the updates, this int91 became available. It's defined in sys.h, and for Intel, you dig down into trap.h and you see that t-syscall_int is pound defined to hex 91. So there's different libc libraries. There's a libc.a for sysenter, a 1.a, a 2.a for syscall, and a 3.a for the interrupt. They all work, right? They're just different methods. If you dive down into the source code for Open Solaris, syscall.asm shows that the int and the farcall methods are actually almost one and the same. They just basically handle subtle differences in the semantics of what that instruction does for the CPU. So like, what exactly was pushed? Did E flags get pushed automatically, or do I have to do that manually so that I can match it and I can have a stack frame that's the same for both, right? So it just kind of handles the idiosyncrasies. Whereas sysenter is kind of a different beast. It has a different basic block in the code.